Hi everyone, welcome back. We're going to be looking at magnetic fields in this series. Magnetic fields are the third kind of field that we're studying in area of study 1 for unit 3, alongside gravitational and electric fields. You should go and watch those videos first. This is typically done at the end of the field section because it combines elements of electric fields with the application side of things towards the end. So go read those videos or read those notes, watch those videos if you haven't done so. Alright, so here's our key knowledge focus for this video. This video is just going to be basically an introduction to the field. It might be a bit long. We're going to be looking at a couple of videos from other people, which will take up some time. So you can have a read of that key knowledge focus straight from the study design. Let's get stuck into it. So what is the magnetic field? So just like gravitational fields are exerted by objects with mass, and electric fields are exerted by objects with charge, magnetic fields are exerted by objects with magnetism. Okay, and if an object exhibits magnetism, you can call it a magnet. Alright, so it's just this property, inherent property of an object. It has magnetism or it doesn't, just like something has charge or it doesn't. Alright, the field unit of field that we're going to be using is Tesla. Okay, it's a bit different to the other units of field that we've studied so far. So gravitational field has units of newtons per kilogram. The electric field has units of newtons per coulomb. But why is this one different? Well, it turns out there's no real quantity that defines magnetism. Generally, we associate magnetism with the field that it produces. Okay, that seems to be the most helpful thing, at least for you guys now. There are other things that you can use magnets for in university level stuff, which we're not going to get into, and you can have a unit defining magnetism. But we're just going to be working with the magnetic field. We're not going to be looking at the thing that makes a magnetic field in terms of a unit. We're just going to be looking at the field, and the field has units of Tesla. Okay. Like we just said, magnetism is an inherent property of a material, and it's got something to do with the way that the electrons are spinning around inside the atoms that make up the material. Okay. Generally, if a material is magnetic, all the electrons are spinning in the same direction, you can say. Okay, it's a bit technical, we're not going to get into it, but that's kind of what's happening. All right, and just like a gravitational field exerts a force on other objects with mass, an electric field exerts a force on objects with charge, a magnetic field exerts a force on other objects that have magnetism. Okay, so again, magnetism is that inherent property of an object. Okay, so let's just watch this short video just to visualize the magnetic field around a bar magnet. So I'll mute my microphone and you can just watch this video. I'll skip to the important parts. Okay, so you can see there's that very distinctive shape that you've probably seen drawn in diagrams of bar magnets back in your junior years. So what's going on here is there's some iron filings, some sort of like little iron pieces. I guess, suspended in a liquid of some kind. And when the iron filings are brought close to or in the proximity of this bar magnet, the little iron filings line up in the direction that the field lines are pointing. Okay, and it gives it that very distinctive bar magnet field shape, okay, which I'm sure you've seen before. Let's move on. Okay, so bar magnets and magnetic poles. So we know already from junior years that magnets have two poles, a north and a south. And you might not know that if you break a magnet in half, you actually get basically just two smaller magnets, okay, each of which have a north and a south pole. And you can keep breaking it in half, keep going and going and going and going and going until you get to basically the atoms. But you'll never end up getting a north pole being separated from a south pole, okay? So a magnet is always a dipole. As of this video being produced, there has been no confirmation of the existence of what we might call a magnetic monopole, which is just a single north pole isolated by itself without a south pole. Okay, so you always have a north and a south end when you're dealing with magnets, especially bar magnets. Okay, shapes. Okay, you've seen this before. I'm not going to spend too much time on it. There's the shape of the bar magnet up there. By convention, the field lines go out of north and into the south pole. Okay, just like for electric charges, by convention, the electric field goes out of the positive charge and into the negative charge. So if you like, you can sort of make the connection in your mind that the north pole of a magnet is very similar to a positive charge when you have this positive negative dipolar charge thing that's going on. All right, so you've seen that image before. Okay, that shows you what the magnetic field around a bar magnet looks like. You can compare it to that video that we just saw. Right, again, we've got a video here showing you the direction of the field around bar magnet and also a horseshoe magnet. Basically, what's going on in this video before we start it is you've got all these tiny little bar magnets suspended in this apparatus, and they're free to move. Okay, they're free to spin around and move around, and basically you can consider them as small compasses. All right, and what's going on is the compass is basically just a small bar magnet that has a north pole and a south pole. When you put a bar magnet or a compass inside a magnetic field, what's going to happen is the north pole of that compass or the north pole of that bar magnet is going to experience a force in the direction of the field, okay? Which is why a compass spins around to align itself with the magnetic field of the Earth, all right? And that's what you're going to see in this video here. So let's play it. I'll mute my microphone.
As you can see, it has 6 acrylic panels around, but you don't see the magnetic field at all. But if you bring it up near the magnetic field demonstrator, you'll see that the little compass needles align themselves with the magnetic field lines. So let's see what the magnetic field lines look like around the whole bar magnet. Now the field demonstrator has a removable panel. You insert the bar magnet, slide the panel back in again, and there we have it.
Okay, so you can see there that what these little compass needles are doing is they are aligning themselves with the field that is surrounding the bar magnet. Okay, and you can see basically each of these little compass needles is kind of taking the role of the iron filings from the other video. Okay, and the iron filings lined up along the field lines of the bar magnet, so too are these compass needles. Okay, and you can very easily see that the field is very much a three-dimensional thing, whereas we're used to seeing the field being drawn as a two-dimensional property, but it is three-dimensional, okay?
The invisible is revealed. So each of the little compass needles are aligning themselves with the magnetic field that surrounds the bar magnet. Now, the convention scientists use to draw magnetic fields is that the magnetic field lines come out of a north pole and loop around into a south pole. Just like the bar magnet did. Actually, you could think of the horseshoe magnet as a bar magnet that's been bent round in the shape of a horseshoe. Lines. Look, here's the magnetic field demonstrator, and we can insert the horseshoe magnet into the side and slide the panel in. We give it a little tap just to get the compass needles aligned, and there we have it. Now let's have a close look at what we're seeing here.
Alright, so there you go. You've seen now that this magnetic field causes these magnetic objects to align themselves with the field. Okay. Alright, so why do they do that? Well, if you're talking about one magnet causing another magnet to experience some kind of force, basically you can consider them almost like charges. Okay, so you've got two bar magnets here, and we've got the north pole facing the other north pole of the other magnet. What's going to happen is the two magnets are going to get repelled from one another. Okay, just like two positive charges would repel each other, or two negative charges would repel each other, so too happens with magnets. Okay, north repels north, south repels south. Okay, if you were to swap one the other way around, so that north was facing south, then the two magnets would get attracted to one another. Okay, so what's going on when we have the compass needles aligning themselves with the field? Basically, the north pole of the little compass needle is getting attracted to the south pole of the central magnet that's inside the apparatus. Okay, another way to think about it is that the north pole experiences a force in the direction of the field lines that that north pole has been placed in. Okay. Okay, drawing field lines. So again, you've seen pictures like this before. You always draw your field lines starting from the surface of your object, and your field lines never cross over each other. Okay, you've got to remember field is a vector. So the field at a point where there could be multiple sources of the field, you need to add the field from both sources vectorially to get a net field at that point. All right. Basically, there's your bar magnet, basic bar magnet. Field goes out of north into south. Here you've got north pole facing a south pole. You've got the field sort of going from north into south. Okay, field's exerted in all directions from the north pole, but you can imagine the field getting sort of attracted back down towards the south pole. And here you've got two north poles facing each other. Okay, you can consider the field lines as sort of being repelled away from the other field lines. Okay, and they're sort of getting this squashing effect that's happening here. Okay, most of the time you don't draw field lines inside the bar magnet itself. Okay, because that's just a solid object. It's just similar to how you don't draw field lines inside the Earth. You just draw field lines outside the Earth. Okay. All right, here's field line diagram for a horseshoe magnet. Again, field lines are going from north to south. Okay, in between, okay, you can consider that to be almost a uniform magnetic field. Okay, but again, you've got that classic picture. Field lines go out of north pole, they bend around, loop around, go back into the south pole. Okay. So you can have uniform field lines where all the field lines are pointing in the same direction and are evenly spaced apart, indicating equal magnitude. Or you can have non-uniform field lines, like basically every single field line drawing for every magnet ever. Like we said before in the previous slide, the bit between the north and south pole of two bar magnets placed like this, that bit in between here can almost be considered uniform, okay, especially if like the width of the bar magnet is much larger than the separation between each of the bar magnets. Almost similar to the parallel plate setup with electric fields. Okay, the bit in between can generally be considered to be uniform under the right conditions. Okay, so some objects are more easily able to be magnetized than others. We call these objects ferromagnetic. Those objects are generally made out of these three elements, iron, nickel, and cobalt, just based on their chemical properties and the way that the atoms interact with other atoms. And if you've got objects made out of these materials, then they can be permanently magnetized under the right conditions. Okay, we're not going to get into it. It's outside the scope of the course, but you can read into that if you like. Just to search ferromagnetism, and you'll be able to read a whole bunch of stuff. Right, now, because the Earth is basically the core of the Earth is basically a solid iron, which is just floating around in molten iron, the interaction between the inner core and the outer core and all these currents that are being produced inside is generally thought to be the cause of Earth's magnetic field. Okay, we're still sort of figuring stuff out about the magnetic field of the Earth, but that's probably the best explanation that we have so far. So the Earth can basically be considered kind of like a giant bar magnet. Okay, the interesting thing though is that if compass needles point towards a certain direction and you follow the north pointing direction of your compass needle, if your compass needle's north pole is being aligned with the Earth's magnetic field, then it must be pointing towards the south magnetic pole of the Earth. Okay, now this diagram's a little bit incorrect. I suggest that should say south magnetic pole because the field lines are going into that place, and the other side should be the north magnetic pole because the field lines are going out of that place. Okay, and that's how your compasses would align themselves on the surface of the Earth. Okay, so the North Pole, the geographic North Pole, should actually be near the South Magnetic Pole if you're sort of using the convention of field lines go into the South Pole. And it's interesting to note that the magnetic poles of the Earth are slightly off-center with the geographic poles. Okay, and in fact the magnetic poles are always changing their location. Okay, they're not generally in the same spot for very long. And every few thousand years or so, what happens is the poles actually flip and they reverse their polarity. So the North Pole would then flip to become the South Pole and the South Pole would flip to become the North Pole. It's all due to the magnetic interactions with the core of the Earth and stuff like that. Really interesting stuff, okay? But the Earth does have its own magnetic field and compass needles align themselves with that magnetic field. So let's finally do a question. We're getting towards the end of the video. So here we've got a bar magnet. Which direction would the magnetic field point at the spots marked A, B, and C on the diagram below? Okay, so you've just got to remember what the field lines look like for a bar magnet. We go out of north and into south. I'm going to rotate my screen. Okay, so you've got basically, if you just draw a single field line going out of north, curling around backwards like that. Or we might draw another one as well. Okay, so we've got 3 points. We've got point number A here. Okay, now because A is directly to the right of the south pole of the bar magnet, that means that the field at that point is going to be directly to the left. So let's use another color. The field line right here would be pointing straight that way. Okay, it's a little bit hard to see from the way that I've drawn my field lines, but if you drew a whole bunch of them, you'd eventually get a field line that basically comes straight in from the right, is almost perfectly horizontal, and would go in like that. Okay, and that field line happens to go through that point A, so A must have a magnetic field pointing directly to the left. All right. Same thing for C. C is sort of like directly halfway between the north and south poles, and at that point, the field lines are going back towards the right here. So at that point C, the field is pointing directly to the right. Okay, straight to the right at that point. Okay, so now we're drawing the field, magnetic field as a vector at each of these points. B is a little bit harder to visualize, but if you had enough field lines, you would be able to see that the direction the field lines are pointing at that point B there would be somewhere up that way. Okay, so there you go. Okay, field lines at different points around a bar magnet. All right, now just before we finish the video, hopefully you've made it this far, there are a couple of ways that we're going to be representing the third dimension. Okay, generally when we're dealing with fields, you've only got up, down, left, and right. Okay, but there's also a third dimension which is necessary because we'll be dealing with a whole bunch of different scenarios, and that's in and out. Okay, so into the page is generally drawn as a cross. Okay, I need to update these notes, but basically we use just a cross for magnetic field, and we use a cross surrounded by a circle for when we're indicating the direction of an electric current flowing through a wire. Okay, same thing with out of the page. Okay, we represent out of the page with a single dot for field lines, or we represent it with a dot inside a circle for electric current. Okay, now the way that you can remember this is think of like an arrow from a bow and arrow. Okay, so you've got at the end of the arrow you've got like feathers. Okay, so if the arrow, imagine taking this arrow and viewing it so that the pointy end is away from you, what you would see is the feathers on this side, and the feathers would make a cross looking shape. Yeah, so that means the arrow is pointing away from you, and if you're looking at a page, away from you means into the page. If you turn it the other way around and you look at the pointy end of the arrow, well, the arrow pointy end is just a single point, and that's a dot. Okay, so if you're looking at the pointy end of an arrow, you're looking at a dot, that means the arrow is pointing out of the page. Okay, that's just a way that you can remember it. All right, that's it for this video. We'll stop there. It's been a long day. I'll see you next time. Next time we'll look at some more sort of quantitative stuff. Okay, see you then.